data frame
是就
之后
我们写
，index 除以6等于0，那就避免了
这东西算0.3，
当然也
当然12题
都讲上
我懒，没写。
20张图，
写的是啥？
我看那个昨天晚上试了几次，我光把它变成 data frame 的时候给我卡了，后面它这个结构是可以，它结构本身是这个 dictionary， 其实是它会是用在这个。
I would start looking at the project more. Yeah, sure, we can do that. Yes. It's because I want.
Can work for me.
Yes, yes, yes.
要我把这个重新按 dictionary 弄了，这个太小，它对应的图片。dictionary
Can people online confirm that I'm audible there?
去前面我给它给背。
Alright.
那只要他们看到这个。
Alright. Welcome everyone. Welcome to Geometry of Data. Today, so we were sort of discussing graph neural networks in the last class. In this class, we'll do sort of wrap it up and quickly get like an introduction to what the graph neural networks are. Very quick, brief, like an introduction to what they do and how they function, like just a basic premise in the first 20 minutes, and then Professor Fletcher will take the rest of the class. So, all right, so let's get started. In general, okay, so we are looking at graph neural networks. In the last class, we had already seen like the basic math of message passing and also why graph neural networks are used, but I'll sort of reintroduce it again for the sake of completeness and sort of use another a new example to sort of make it clearer to you about what we're trying to do here and what kind of data we'll be able to process with a neural network like this. So imagine that you have the task of a few friends in the real world, right? So there's a lot of people in this universe, on this planet. There's different people, and there's a social network of people who sort of engage with each other and sort of communicate. And what you have to do is sort of match people around in a way where you're able to come up with an ideal match in this population based on the traits of the people that you have in the population, right? So imagine that you have a task like that. So how would you sort of go about doing it? So for example, let's look at one person as an example. So let's say we want to match someone named Andy here, right? So what we want to do is that you have a graph node which sort of represents a person in the real world named Andy. And what you want to do is that you want to match this person with another person based on different traits that you're sort of trying to take into account while doing in this process. Okay, so the first thing that you do is that you sort of represent that node in terms of different traits or different qualities that you think are important for a task like this. So for example, let's say you make like a list of things that sort of describe this node. So let's say you say that they're 25 years old, male, other things like, let's say, cannot dance, likes fiction, and other things like that to sort of describe this node as exhaustively as you can, right? So once you're able to sort of describe all of these nodes based on the traits that you want to sort of take into account in this process, then you can sort of play a Cupid and try to find out other nodes which have like similar, you know, like similar traits in a way that you can say that these two nodes are closer to each other as opposed to other nodes. In addition to this, you also have relationships that Andy has with other nodes in the world. So for example, there is a different, let's say a friend named Sam who is in the same social network, and things like that are also present as an input to your algorithm. So your algorithm, in addition to having nodes that represent individual people and the traits of these individual people, you also have edges that connect these nodes to other entities like Andy, who also have their own set of traits and their own set of descriptors of their personality, right? So what you're trying to do is that given a large graph like this, based on only the connection and the traits of these graphs, what you're trying to learn is that you learn an intrinsic representation of the data and how it's distributed and how it's structured in a graphical format so that you can then compute similarities between nodes or do other kinds of math that sort of help you solve different tasks which are related to sort of diagnosing the nodes or the edges of these graphs, right? So for example, in this case, when we are looking at an example of matchmaking and we are trying to play Cupid, what you're trying to do is that you're trying to find different nodes that exist in this universe, and what you're trying to do is that you're trying to establish new connections that sort of connect the node Andy to another node. So what you're trying to do is that you predict traits and features of all of these nodes and eventually try to predict where a new node can be formed, right? And where a new edge can be formed. So if you predict that there are a certain number of people that sort of come into a certain radius of this node, then you can sort of start to establish new connections between these nodes. Okay, but how do we do this like step by step? Let's just sort of go over that once. So now that we sort of understand why a graph neural network is important, because there are other kinds of data that is more structured in a way. So for example, if you have to process images, images are already structured into pixels, which have multiple channels, and these are already a very structured form of data representation which you get as images. And these pixels can then be processed using specific types of neural networks like convolutional neural networks, which sort of identify patterns in local regions and try to quantify that and sort of learn larger patterns hierarchically by applying multiple layers of neural network algorithm. But not all data has the same structural properties. Like for example, even with text breaks down into its components different from how an image would break down into components. For example, language is represented in text, and text breaks down as tokens. And then you have to sort of come up with a new type of mechanism or a neural network architecture that sort of is able to deal with data like that. So anything that is able to deal with data, which is sort of represented in a graphical format, is what a graph neural networks sort of try to do, is try to analyze data that is inherently in a graphical format, which is a lot of data exists as graphs. Like for example, the one that we see now is like a social network, which completely exists as graphs where edges are relationships, right? So for problems like this, you need like graphical understanding. So once you have some information about the graph and the problem that you're trying to solve, like matchmaking here, what you do is that you now need to sort of, once after identifying the traits that you want to sort of take into account, you want to create embeddings for these nodes where each node is sort of represented by a vector, which sort of tells you an embedding or a representation of the properties of that node, right? And this is what you're trying to update after each layer of message passing through the network. And eventually, if you update it like sort of long enough, and based on a certain objective that you want to update these for, you will then get these representations to sort of start having a semblance of some kind of structure that is inherently present in this graph. Like based on the relationships between two nodes and based on other things that you're already sort of embedding in the graphical data format, will sort of start getting included in the information that is represented by these nodes. And how do you do this with message passing? Are there any questions? Yeah.
Oh, I'm just, so can you just remind, like, what is the difference between that matrix and the vector representation?
Yeah, so the matrix or the traits that you represent can be in any abstract format. Like for example, this doesn't have a consistent data type. Like some of the nodes, some of the information is present in text, whereas some is numerical. So what we're trying to do is that convert all of this information into one numerical vector, which is abstractly representing all the information, but does not really have columns which represent each column sort of representing one thing. So for example, in this vector, what you expect is that all of these properties in relation to each other get embedded as a numerical vector. So that people who have similar properties, their vectors are closer. So if you take a cosine similarity between a node A and a node B, and their properties are similar on the basis of our understanding, their nodes, their vector representation should also be closer. Like the cosine similarity should be sort of higher as opposed to nodes that are very different from each other.
And the vector is like, is the thing that being learned, right?
Yeah, so the vectors are the things that you're trying to learn, and we'll see how you sort of update these vectors as you do message passing. So, like if you recall, the different types of neural networks have different layers, right? So the first layer of a convolutional neural network sort of looks at very small regions of the image and sort of contextualizes those patterns into a numerical representation. And then you do it layer by layer, and these representations keep getting more and more complex. Similarly, for a graph neural network, what you do is that you do multiple rounds of message passing. And one step of message passing is described as such. So imagine that you are doing this message passing is done through, like, let's say a function f. And what you're trying to do is that you are trying to update the node Andy by taking into account all of its neighbors. Okay. So let's say these are its neighbors. This is node 1, so node 2, and this is node 3. Right. So what you want to do is that, let's say v Andy is this. You want to update the representation of this node Andy using a function f, which takes into account all of these nodes x1, x2, and x3. And only x1, x2, and x3, because these are neighbors, are directly connected to your node Andy. There must be other nodes as well, which maybe are connected to, let's say, Sam, or this one may also be connected to 1, but it's not directly connected to Andy. So you're only taking into account the neighbors that you have, and and you do this message passing not only for Andy, but for every node in your, let's say, graph, right? So you're updating all of the nodes at the same time. So all of these representations will get updated based on their neighbors, and this node will get affected by this neighbor, and by proxy, the Andy node will also get affected by that neighbor because this one is getting affected by that. So that is how the message is passed. Like if you had like a connection is 2 nodes away, the message sort of indirectly passes, and the information is sort of like indirectly conveyed to that node. Okay, so your v Andy needs to be updated based on a function of x1, x2, x3. All 3 of these sort of also, and now just trying to sort of contextualize a little bit more what this function would look like for a basic graph neural network, but there are many ways to sort of come up with functions like that, as long as the function is like does not take into account the order of the nodes. Like as long as it's if you pass x1, x2, x3 or x2, x1, x3, the output should be the same. There's no sense of which node comes first. As long as your function is something like that, this would work in a graph neural network context. Okay. Now the function, for example, if we take like let's say mean function, which would just take all of the nodes which are like your neighbors and just take a mean of those nodes and then use that as the updated embedding, that would just look like this. So let's say you have a weight C11, which is the node between, sorry, let me write A1, which is the node between this node A and 1. So this is C A1, this is C A2, things like that. So you multiply the weight of the edge with the value of x1. Similarly, do the same thing with x2 and do the same thing with x3, right? And if you pass this through, let's say, a nonlinearity, which is the sigma function, this is completely a valid way to write a graph neuron. And if you do this again and again and again, by sort of iteratively updating all the embeddings of each of the nodes, and then eventually using the representation of this embedding, let's say. So now the problem is that you are updating this, but with respect to what, right? Because once you sort of try to update these embeddings, you also have to sort of update it to sort of optimize on a specific objective function or something like that, right? So based on what your problem is, you then come up with an objective function which would sort of add some information or structure to the learning process of the graph. So here, because we sort of using an example of a matchmaking problem, the objective would then be that you, number one, observe real world relationship data for the nodes, right? So what you do is that you observe like actual data in the real world. Like for example, you're trying to solve like a matchmaking problem. So here, all of your edges should represent like a relationships that Andy has, or maybe sort of have some sense of how much time he's willing to spend with these people, so that these edges mean something, right? And once you sort of add that kind of structure, what you can then do is that sort of come up with an objective function which sort of minimizes the distance between points A and D, and anyone say minimizes the distance between X and D and X J for every J that is a set of people that handle, right? So what you do is that you sort of observe it in the real world, try to find out who is closer to this node, and then based on trying to optimize those distances, you start updating these embeddings. So eventually what will happen is that these embeddings will become such that embeddings that are closer to each other and people that sort of really associate with your target node will start getting embedded closer in the embedding space. And once that starts happening, you will already start getting start automatically learning the structure of this type of data representation. And then eventually, once this process is complete of message passing and then iteratively updating all the nodes, you can then sort of just randomly create a radius around randomly and then establish new nodes between all of the points that like all of the establish new relationships between all of the nodes that appear within that radius of a certain target. And this then becomes a edge prediction task because you're trying to predict an edge between two nodes that don't really have an edge already. If let's say you do a problem which is similar to this and try to predict who let's say who would do which based on the traits of each of the nodes, you're trying to predict who would be in what profession, let's say. Like for example, you take all the nodes that sort of represent this specific person, and then you pass it through a neural network, and that it predicts like what kind of profession this person would have. And that neural network would then be a node classification task because you're trying to classify each of the nodes of this graph. And in that case, what you would do is that after updating these embeddings, after a message passing around, you would pass the embeddings individually to the objective function, which would sort of optimize the model for predicting the correct classification in terms of the profession. So things like that are possible. If you want to sort of predict the overall classification of the graph, like take one representation of which sort of represents the entire graph, you then have to sort of aggregate all the nodes and get one representation that is representing the whole graph, and then that becomes sort of a graph classification problem, right? So there are, depending on what your problem is and how the data is represented. This is how you sort of maneuver data into a graphical format and then sort of either solve an edge prediction task or a node classification task or even a graph classification task. All right. Okay, so that was just a very brief sort of introduction to graph neural networks. I'll sort of stop here and pass the mic to Zubeda for the rest of the class. All right, it's been great teaching you guys for the semester. Yeah, thank you.
All right, now, so y'all are stuck with me for the rest of the lectures. Which is just the end of this lecture and then Thursday, and then we're gonna hear from everyone and their final projects next Tuesday. Let's see, maybe a couple just reminders that the final homework is extended till tomorrow, I believe, if I remember correctly, till tomorrow, the usual time, 1 minute before midnight. And then hopefully everyone is making good progress on their final projects. And just a reminder that a week from today, we're going to do presentations. Everyone's going to do presentations here. I guess we'll have a announcement about the logistics of how to do that. I think there's about 15 or so projects being presented. I'll have to check my count on that, but we have enough time for everyone to take about 5 minutes with maybe, a minute or so for transition, but we need to be kind of efficient. Everybody coming up, getting ready and just going quickly. One possibility is that if people send me a PowerPoint or PDF like slideshow, it'd be quickest to just use this computer here because it's connected, ready to go. If you absolutely have to use your laptop for one reason or the other, I guess we can hopefully get that to work. But you might want to come and test out your laptop, connect it to one of these dongle-y things here, cables here, and make sure you can project sometime before class on Tuesday. So I'll send an announcement about all this, but just kind of a heads up. You might think, oh, my laptop just connects to stuff easily, but you'd be surprised if you haven't used this technology up here before. It's good to just check it. But the easiest, safest thing would be to send me a PDF or PowerPoint or some such, and we'll put it on this computer before class, so you'll be ready to go. Any questions on anything with class, like the homework or the final projects that I can quickly? Yeah.
Like what order do we go?
Good question. We will come up with some random ordering of you, everyone. When maybe I can. I don't know if it matters too much because hopefully everyone will be here, but we can maybe email out that order before Tuesday. But yeah, I'll just take all the projects and do a pseudo random number generation to order everybody. Oh, so there's not a final project link. What the chat is saying. I think you mean in Canvas or. Oh, you mean on the syllabus? Yeah, sorry. Shoot. Yeah, then I will fix that. I probably put in the link, but then messed up the git commit of the PDF. Thanks for pointing that out. I should check that these things actually work successfully. Okay, yeah, I'll fix that, but it's the final project is what you would imagine, like what we talked about for a PDF. Or sorry, a report and then a presentation. And yeah, I just have kind of like things to kind of like, you can just check off like, yeah, we we explained our algorithm, we, did all our experiments and showed the experiments. You upload your code, if there's any code you wrote. If you're using other people's code, you don't have to upload it, but reference it, this kind of thing. But yeah, so thanks for pointing that out. I'll make sure the PDF is posted correctly at the end of class today. Okay. Get the camera to hold correctly. So today and Thursday for the last 1.5 lectures, I'm going to be talking about information theory. And related topics within there. Main concept in information theory, that the basic principle behind all of it is this concept of entropy. And then we'll also talk about the Kovac-Wheeler divergence, which has come up in the class a few times. And we've defined the equation, but haven't really dived into what exactly is it and what does it mean, and kind of the way to think of it. I think I'm maybe misspelled Wheeler. Maybe EI. In my notes, I have EI. Could go one. IEEI, one of the others. How many people have learned, maybe in a previous class or just studying on your own, things about entropy in the realm of information theory? Okay, so not so many people. Yeah, so just the history of information theory and this concept of entropy I'll mention first. So information theory really comes out of communications. And so this guy named Claude Shannon wrote this paper in 1948 that introduced sort of the whole field of information theory. He was working at Bell Labs, which is kind of like with AT&T, was very much interested in, of course, communications. And the concept of entropy is really about digital communications. And this really set off the digital revolution, arguably, amongst other things. But the ability to transmit digital information over communication channels is what makes it possible for everyone who's currently on their laptop or their phone right now, and everyone that's on Zoom right now, to be able to do what you're doing, Wi-Fi, your 4G, 5G, wireless communication, digital, everything you watch on TV or listen to on the radio. These days, it's all digital communications. And so really our modern world was made possible by this field of information theory. So 1948 is roughly when it started with this guy, Claude Shannon, who's not really a household name like Einstein or, other famous, scientists and mathematicians, engineers, but maybe he should be given what he contributed. Now you might be wondering, this sounds more like, information theory, communications, doesn't sound like anything we'd be studying in geometry of data, machine learning class. But it turns out that all the topics that came out of information theory were also very critical in machine learning and specifically modern deep learning. And we've seen this, like I said, bubble up from time to time. You didn't maybe know that it was from this communications theory, communications kind of field. But the KL divergence we've seen in a few places, and entropy also comes up without the KL divergence aspect there. So just to mention an example that you probably have heard, at least if you haven't thought too much about, when you train a classifier, maybe I'll ask the audience, if you train a classifier where the output is discrete labels, like categories, right? What is the usual loss that you use to train a classifier?
Cross entropy.
Yeah, cross entropy. So you have a binary classifier, you have binary cross entropy, or more than 2 classes, you just have softmax followed by a cross entropy loss. Okay, And that word entropy is not a mistake. It's not that you see it here. It is what we're going to be talking about that came out of information theory and communications back in 1948 and later. And then the KL divergence. Okay, but since I'm asking the audience questions, let me keep going. How many people can tell me, there's multiple places this has come up, who could tell me what topic in the semester we've seen KL divergence? Just maybe one of the topics we've seen it. Does anybody remember? This is a real, have you been paying attention this semester kind of question. I probably wouldn't, if I was in class, no, be able to do it myself. I know because I was teaching the class, but can anybody think of where you may see KL divergence? Yeah.
So I guess, was it on the first homework where we saw like in the higher dimension, the mean was left skewed?
Sorry, wait, I'm not remembering, when we saw what in the first homework, which.
So that was the last question, like in the higher dimension, we're trying to plot the angles.
Oh, right. That's a good, yeah, there might be a KL divergence linked to that, but that's a good question. It's not explicitly in there, but that's a good guess. There may be a KL divergence thing going on there, but not that I can think of explicitly. Yeah. Anybody else have a guesses are welcome for sure.
Maybe Lee group, I mean, because I think, Lee group is GL, I think.
Yeah, that's generally you're not KL, yeah. Yeah. Close on the letters, the acronym. Okay, so if there's no other quick guesses, I'll give you a couple examples. So one place the KL divergence came up was in variational autoencoders. It's kind of the key ingredient to variational autoencoders that take you from just an autoencoder to a variational autoencoder. We're going to kind of make that link kind of very clearly by the end of Thursday, if not get to it today. The other place it came up was in diffusion models that Aman presented. So the thing you minimize the loss in diffusion models, you have this forward process where you're adding noise, and then this reverse process where you're sort of trying to undo that, remove the noise and generate a random image. It minimizes the KL divergence between sort of, you know, the noising process and the denoising process there. Let me see, I think I had another example, but I've now forgotten where KL divergence comes up. Anyway, but yeah, so the point I want to make is that all this information theory stuff, even though it seems like old school, like electrical engineering type topics, it's actually very highly relevant, like stuff that's coming out, you know, as we speak in machine learning. This is kind of a core backbone of a lot of that methodology. Okay, so yeah, so let's go over. So the goal, yeah, is to go over the basics of what is entropy mathematically, what is KL divergence, again, mathematically, what's the intuition for what's going on there, and then to kind of revisit some of these topics we've talked about in class and kind of tie them together with how this information theory concepts come up there. Okay, let's see, cameras follow me. So let's start with the foundation definition here is entropy. And so I'm going to talk about the entropy of a random variable. And what I'm going to do first is I'm going to start with just the discrete case, because you kind of have to treat discrete and continuous a little bit differently here. And entropy is really, when we just say the word entropy, we typically mean for a discrete random variable. When you're doing cross entropy, right, in machine learning to train a classifier, that is a discrete labels. And then you get what we're going to talk about right now. Okay, so entropy is usually written with this H of X, By the way, entropy, the word entropy comes from physics, if you know physics, and thermodynamics and things like that. There's this physical concept of entropy, which is kind of like disorder or chaos, if you will. That's my very limited way of explaining physics. And it's somewhat related probability definition of entropy, but there's nothing physical about it. Let me just give the equation first, and then we'll try to parse it and make sense of it. So it's the expected value under the distribution of, let me say, of a random variable x. It's the expected value under this distribution of x of minus log p of x. Okay, to take the probability, and now x is a discrete random variable, so p of x is the probability of a particular discrete outcome, right? This is the probability mass function. You take the log of that, and this is number 0 to 1, you negate it, and then you take the average over all possible outcomes of x. Okay. And because we're right now sticking to discrete, I can write this down. The expected value is just the sum over I. Let's say I are all the possible outcomes of x. Then I have probability, or I should say, let me write it as xi are all the possible outcomes of x. This is what an expected value looks like in the discrete case, right? I just take the probability of the outcome, I multiply by the thing I'm taking the expected value of, which is log p of x, minus sign out here, and that's what we're doing. Okay, so pretty simple formula. Let's take a look at, actually, let's take a look at, first of all, what is this function that we're taking the expected value of minus log p of x. If I plot it as a function of p of x, just to get a sense here, right? From 0 to 1, p of x is a probability, so it's 0 to 1. And of course, if p is 0, log of 0 is minus infinity. So this thing kind of asymptotically goes to, and I'm negating it so that this goes to infinity as I go there. And of course, as I come down here, log of 1, okay, I didn't quite, in there is 0. But you have this kind of picture. Okay, that's a little bit better. That's minus log of p, right? And so as I have outcomes with various probabilities, I'm going to evaluate p of x or minus log of p of x and sum that all up. Okay. Okay, and so what exactly is entropy here? What's it doing? You will often say this is the average amount of information that the random variable x is providing. So minus log of p is like the information. It's also called the surprisal sometimes, like how surprised should I be? So if you look at minus log p, you can see why it's called surprisal. Low probability things have a high surprisal. If it's a very high probability thing, like if it always happens with probability 1, you're not surprised at all. 0 surprisal at probability 1. Okay. So the more probable events are, outcomes are, the less surprising they are. The less probable they are, the more surprising they are. Okay. If you see a high probable thing, so why is surprisal and information kind of the same thing? If you see a high probability thing, it's not much information gain. If you're just observing events, okay, then it's you don't gain much information. Every time you see something very low probability, you gain a lot of information from observing that. Okay, so you may have not known this was even a possible outcome, but you see it very rarely, and when you do see it, you gain a lot of information about what can happen in this system, let's say. Okay, so that's kind of the intuition for just the inside part here, the thing we're taking the expected value over. It's like surprisal. So if you go back to 1948 and think like Claude Shannon, you think you're on one end of a communications line and someone's transmitting information, let's say data rather, over a channel. So you're receiving bits or you're receiving characters in like a text. The amount of information you see or how surprised you are about what you end up observing can be kind of quantified this way. Okay. So you think about English language, right? Let's make a kind of concrete example. And you think about just the characters, A, B, C, D, E, F, G, etc. If you see an E, it's a very common character in English language. It has very low information content, low surprisal. If you saw like a Z or an X, let's say, that happens much less often. It would end up farther on this spectrum and you would get a high surprisal for seeing a character like that. So that's kind of the idea. Okay. Any questions so far? That's the basic definition of entropy. Okay, let's take a look at sort of the simplest example of a random variable. As I always like to say is the Bernoulli distribution, just a binary random variable, 0 or 1. And again, this is what we use for a binary classifier as the labels, for example. So it is relevant for machine learning, but it's also relevant just as like a simplest example to start with. And let's think about what is entropy in terms of a Bernoulli random variable. So Bernoulli random variable, remember, it's just one parameter. We were calling it theta before. This is just the probability of a 1. And 1 minus theta, and it's number 0 to 1, right? 1 minus theta is the probability of 0. Okay, now let's specifically look at a fair coin, meaning, 50-50 heads or tails. So theta is equal to 1/2. Okay, and think about what is the entropy of such a distribution. Okay, so h of x is equal to the sum of the different outcomes. Actually, let me just write, we know the outcomes are either 0 or 1, so I won't write it as a sum. The probability of 0 times the log probability of 0, put the minus sign in, minus the probability of a 1 times log probability of 1. Okay, let me, because I'm doing binary things, put a 2 base on my log. Notice I didn't put a base on my log over there. I kind of left it ambiguous, but let's do it base 2 for purposes of binary things here. And of course, the probabilities are all 1/2. The log base 2, right? Of 1/2 is a -1. So that just changes the sign to a +1/2. And this is the same thing. This is 1/2 log base 2 of 1/2 is -1. So I get 1/2 plus 1/2 equals 1. So the entropy of coin flip is 1. Now this gets us to the next kind of concrete intuition for what entropy is doing. So if I wrote the surprisal in log base 2, I really should keep the -1/2 with that. What I'm doing is I'm saying how many bits of information I'm getting from my coin. Okay, so we say this type of information we declare as bits. And notice that this checks with our concept of bits in general, which is that if I give you a coin 0, 1, right, the amount of information you're storing by that 0, 1 is 1 bit. Okay, so that checks out. If we were to do flipping 2 coins, then you have 4 outcomes, right? You can encode 0, 0, 0, 1, 1, 0, 1, 1 are the 4 outcomes. Each of those outcomes, if they're fair coins or fair binary bits, random bits, is 1/4 probability. And you get 1/4, you can just do the math, you sum up 1/4 4 times, and you, this becomes one. You sum up 4 times 1/4, and you or sorry, 4 times log 1/4. Log 1/4 is -2, so it doubles. So it's 8 times 1/4, and you get 2. You get 2 bits, which also checks out. Okay, so and in general, you keep going. If I gave you a K Bernoulli outcomes in a binomial distribution, all of probably 0.5, you get K as the number of bits of information for entropy. Okay. So that checks out. And now now let's do the case where theta is not theta is anything, I should say. So theta is anything between 0 and 1. Okay. I won't write this out. I'll just plot the function. This is now again just a single x Bernoulli random variable with probability theta of a 1. What you end up looking at if you plot this function h of x, where it's this thing, and now p of 0 is theta. Sorry, wait, that's 1 minus theta. Log 1 minus theta, and this is log theta, not just 1/2. Okay, that function looks like the following as a function of theta. Oops. Theta again goes from 0 to 1. It looks like this, where at the endpoints you're at 0, at 0, 1, and at 0.5, we just saw what that value is. That value was 1. Okay. And so what does this graph tell us? It tells us that this function looks kind of like sort of like an upside down parabola. It has a peak at probability 0.5, and you have 1 bit of entropy for a fair coin, if you just saw here, and that's the most entropy you can get. Okay, the most uncertainty or the most average information or surprisal you can get is if you have a fair coin, because you have no way of predicting each time it comes up. You're always 50-50. Every guess is as good as any other. That's kind of the maximum entropy you can get. If you have a coin that shades to 1, let's say it's like 0.75, then you're going to get something with less entropy. Okay. Another way of thinking of that is how predictable is the outcome. If I have something that I know has a 75% chance of a 1, I should always just predict 1, and I'm going to do better than if I try to guess 0 or 1 by some magical method. There's nothing better I can do than just always predict 1. I have less information every time I see something because it's more often going to be a 1. If it's always a 1, 100% of the time, I get no information. Seeing a new bit, it's always 1, doesn't tell me anything. It's just always going to be 1. I know that. It's perfectly predictable, no surprise. Okay. So this is kind of the way to think of entropy in terms of information, predictability, surprisal, if you will, uncertainty are all words you hear around the topic of entropy. And this is kind of everything you can do with just a simple binary random variable in terms of entropy. Okay. Any questions? Great. I'll mention one other thing that we're going back to, again, 1948, Claude Shannon, and coming up with this idea of entropy. It was kind of really the mathematical foundation, again, of communications. The famous theorem that Shannon came up with, sometimes called the Shannon coding theorem, is that the entropy of a random variable, and when he was talking about random variables, he meant that the thing, the signal or the channel you're communicating over, the stuff coming across was this random variable X. That's the entropy he's concerned with. But he has this very famous theorem, Shannon coding theorem, that basically if you try to take a message and compress it, the best you can do over a perfectly noise-free channel, like let's say I can transmit it and not worry about it getting corrupted. The most compression you can do such that at the other end of the channel, you get the whole message. The lowest you can compress it is by the entropy. That's the average, I should say, in the limit over all the bits you're transmitting. They can be compressed down to their entropy. Okay. So if you try to transmit a signal that's just 0, 1s, random coin flips, you basically can't compress, is what this Shannon coding theorem says. There's no rhyme or reason to whether it's going to be a 0, 1 coming across, so there's no way you can compress it. But things like the English alphabet or other languages also, if you will, is that we have higher probability of some characters than others. And so if you just look character by character, you can compress based off of the probabilities, the frequencies those characters appear in messages. And they can be perfectly come across the other end. And anyway, all of that, again, this theory, there's a lot more to it, obviously, in the communications. I'm not going to dwell on communications anymore after this, but all that theory made the possibility of you being able to watch a video on YouTube super fast stream, like, instantaneously over, Wi-Fi or over, your wireless cellular signal possible. Like, we wouldn't be able to do all these modern things we'd like to do without this kind of coding theory. Okay. Right, so let me just make, sorry, I wonder if this is oh, Shantanu, good job. He came up with variational autoencoders. I'm sorry, I didn't see your answer. So someone did see Kale the versions before in the semester. Okay, so let me do just one more thing about entropy to again give us a little bit of a feel for what it's doing in probability distributions. And also, I should say, another application of it in probabilistic modeling and machine learning. So there's this idea of what's called maximum entropy distributions. And basically what this means is that if I give you a class of distributions and say, you have, maybe some parameters and you can choose under this set of constraints, any distribution you want. Now let's try to, over that class of distributions, find a distribution that maximizes entropy. Okay. So let me just give an example and I'll explain why this is a thing we might care about. So first of all, let's just do a standard discrete random variable X with outcomes, let's say X1 out to XK, so there's K possible outcomes. And these outcomes have probabilities, of course, whose probability mass function, P of Xi. Let me write that as PI for short. Then the entropy of this random variable is the following. It's just the sum I of PI log PI. Yeah, by the way, I guess I forgot to mention log base 2 if you're doing communications of digital signals. If you're doing probability for machine learning, typically the log here is the natural log base E. So I should mention that. So there for, hang on, sorry, camera. Over there, so for bits, we said log base 2, we call it a bit, every unit over there. Here, if you did a natural log, you would call it nats, NATs, which I think is fun word to use for some measure of information, nats. is the unit here. Okay. So yeah, so we have the entropy that looks like this. So I want to maximize over all possible distributions, so all configurations of k values, pi. The pi set between 0 and 1, there's that constraint. There's also a constraint, of course, that they sum to 1. Right, they have to sum to 1, and they have put in both constraints. So all these pi's have to be between 0 and 1, and they have to sum up to 1. Okay, but other than that, I want to maximize this quantity. Who can guess based off of our first binary thing over there, what distribution we're going to find maximizes this? Sorry, someone said it.
Uniform.
Yeah, uniform, that's right. So uniform is the answer. You can do this. I'll just give the really quick sketch of how you get the uniform. The usual way is, right, to take the derivative of this with respect to pi's. And this is like a gradient because it's a k-dimensional vector. But take a gradient of this thing with respect to pi's, that vector of pi's. And I have to handle this constraint over here. I'm going to use Lagrange multipliers. If you remember those in calculus, put a Lagrange multiplier on this constraint. And then set that equal to 0. The gradient equal to 0 is where you have a critical point, and in our case, it's going to be a maximum. And then you solve. Okay. And so that looks like the following. I need to set to 0 the gradient, which is going to be the ddpi's of the this equation up here, sum of pi log pi, and then I'm going to do plus Lagrange multiplier lambda times this constraint, that the sum of the pi's is equal to 1. So thing like that. Okay, so that's the thing you take a derivative of and maximize. Trying to debate whether I actually do it or not. Let me just say that if you do this, actually, sorry, I should do a different index. Let's make this a j. Because I is the index I'm multiplying, or sorry, summing in my summation here. So pj with respect to one of these p probabilities at a time. If you do this, you know, the derivative of this thing with respect to pj is only going to be for the I equals j term in the sum, is the point. So this actually is not too hard to do. Same thing here. You're only going to take a derivative with respect to pi where I does not equal j is going to be 0. So you only have a term here where there's a pj. Okay, and so if you do that, the derivative of this is 1 with the pj term. The derivative of this is just simply minus log pj. So derivative of the first term, which is just 1 times this. Derivative of the log p is 1 over p. So you get a p over p, which is just 1. And the derivative of this is just lambda. Okay, so it's not that hard to do. And now if I solve this for pj, and again, let me say this is a natural log. This whole thing, this thing equal to 0. Solve for pj is that pj is equal to 2 to the 1 minus lambda. And the main point here, lambda, remember, is a Lagrange multiplier, which when you do Lagrange multipliers, you have to then figure out what's the lambda that makes the final thing work. It makes it satisfy this constraint. And notice that pj doesn't change with j. So all the pj's, doesn't matter what j is, have the same value. So the only lambda that works here is the lambda that makes this 2 to the 1 minus lambda equal to the constant 1/k, which is what sums up k times sums up to 1. Okay, which again, uniform distribution. Okay, so if you maximize entropy over all possible discrete distributions of k outcomes, you get a uniform distribution. That's the distribution that maximizes entropy. And again, intuitively, this makes sense because it gives you the most uncertainty of anytime you have like modes or peaks popping up in in this discrete distribution, that would be more surprisal, right? And you want to spread that out over, sorry, less surprisal. The higher probability things would be less surprisal, less uncertainty, if you will. And so you want to kind of spread the uncertainty across the whole distribution. That gives you the maximum entropy. Okay, so if you don't get anything else from this last lecture and a half, as far as entropy is concerned, just think of entropy, it goes up the more spread out and evenly distributed a random variable is. Okay, and the peakier it is, the more concentrated it gets around certain values, makes entropy go down. Okay, there's nothing else from entropy. Okay, any questions? That so far? All right, and then the last part here is let's talk about briefly. This is all discrete. What happens in continuous case, which is what we are very often dealing with when you do things like or generative models that we've talked about, the VAE or the diffusion models, I should say. We're typically working more continuous values, and there we can also define entropy, but we have a little bit different name for what we call a differential entropy. Differential entropy. And now X is a continuous random variable. And it has a probability density function, PDF, which I'll just write as f of x. Just to, I could call it p of x again, but just to really distinguish it from the discrete case. And now it's still going to look very similar to this. It's still, wait, let me write h of x, the differential entropy is still going to be an expected value of negative log, usually now almost always at this point, base E of natural log of the density function. So again, kind of very similar analog to that. Density function just replaces the mass function. And of course, this looks like an integral. If this is a real valued thing, then I'm going to do just over the whole real line of PDF. I integrate f of x times log of x. Okay. So that's my continuous version of entropy, and it looks like kind of what you'd expect based off the discrete version. So let me give a couple of examples of, again, max entropy. So max entropy, if I want to maximize h of x, again, I can't just say unlimited, any random variable in the real line, maximize the entropy. Because what it would try to do is give me a uniform distribution over the whole real line, which of course you can't have because there's no height value to f of x being constant that wouldn't integrate to infinity, and it has to integrate to 1. So there's really no such thing as a maximum entropy distribution on the whole line unconstrained. But I can put some constraints on it to make it make sense. I can say such that x outcomes have to be within a finite interval, a to b, and then, as you can guess, this is going to lead to now a uniform distribution on the interval A to B, and that is well defined. I can also play other games. So I can say, what is the max entropy distribution? Such that now I'm not going to constrain it to be the whole real line, but I'm going to constrain it such that the expected value is, let me see, I think I want to use a, character. The expected value of X is equal to some fixed value. So look at all distributions. Actually, this one, you need to say and X is greater than zero. With only the positive half of the real line. If I constrain myself to only distributions with a particular expected value, so mean, if you will, this means that I get the exponential distribution with rate parameter lambda. And then finally, the one that comes up the most in our world, if you will, is now maximize entropy of random variables such that the expected value of X is equal to mu, some constant mu, and the variance of this random variable is equal to some constant sigma squared. And you can probably tell by my notation that this is going to give us what? Yeah, Gaussian. So the maximum entropy, if you specify the mean as a constraint and you specify the variance as a constraint, the maximum entropy you can do is the mean, or sorry, Gaussian normal distribution with that mean and that variance. So let me kind of put a finer point on it with the drawing. If I tell you my distribution has to have a mean at mu, and it has to have a particular spread to it, written in terms of the variance, then the Gaussian is kind of as spread out or maximum entropy you can get by constraining the mean and variance of your distribution. Okay, it's one of the properties that make the Gaussian sort of the universal distribution we use for everything in terms of continuous random variables, is this max entropy property. Excuse me. Okay, I'm not gonna, obviously, I have, a derivation of one or two of these, but I'm not gonna do it. It's actually, if you go to Wikipedia, look up max entropy, there's, I think, derivations of these, if I remember correctly, if you're interested in math, but it's the same kind of trick. It's like a calculus of variations where you take a variation of this problem, of this entropy and put a Lagrange multiplier, same as we did the discrete, just a continuous version of that. Okay, any questions so far? So yeah, so max entropy, why is this important? The first thing is just as some examples of distributions where you have to get, again, more of a feel of what it means to have entropy is, again, kind of spread out. So that's where we're getting the uniform distribution. And the Gaussian distribution, again, is as kind of diffuse of a distribution you can get if there's a particular mean and variance to it. But the max entropy distributions also come up in probabilistic models, Bayesian models specifically, where we very often will have, the whole idea of Bayesian models is that the parameters of your distribution are also random variables, and we put a prior distribution on those random variables, on those parameters. And so maximum entropy distributions are often used as the prior. And why is that the case? So there's this concept of non-informative prior. So if you want to model a parameter and you don't want to inject any kind of information or as little information into the parameter as possible before you actually see data, then you want to have the least informative prior. The least amount of information is the maximum amount of entropy. So if I gave you a continuous parameter, and let's say I could at least pin it down into a certain range, like I know that parameter has to be between A and B, then a good prior to use if you don't want to inject any more information into it is just the uniform prior over that range. If I had a little bit more information about my parameter, and I could at least say, I think the mean should be roughly here, and it should have roughly this variance, this spread, then I can put a Gaussian prior in my parameter, and that's the least informative I can do. So this is one of the applications of entropy and max entropy. I will mention that, kind of a side note, we haven't done much Bayesian things, but in Bayesian statistics, you can, and machine learning, you can do priors, uniform priors over the entire interval, or sorry, the entire real line, which is not a valid probability distribution. So you do P of X equals 1 and X is anything on the real line. But when you put it together with the likelihood and get a posterior, it very often will still be a valid probability distribution when you use Bayes' rule. And so you can take priors, which are technically not probability distributions themselves. Max entropy, again, uniform over the real line as an example, comes up. And in fact, that also comes in from the Fisher information that we talked about. The Fisher information for a Gaussian gives you a uniform prior for the mean, which is not a valid probability distribution, but actually works as a prior. So anyway, these are things that come up in this entropy kind of area. Okay, so moving on. Yeah, I think in the last 5 minutes, I'm just going to set up a reminder. Well, let me think. These are, let me define Kullback-Leibler divergence. We've already defined it, and just give a reminder for why we like it and care about it. And what it has to do with entropy. We leave that here. And sorry, camera. There we go. So that we can keep that equation, the E minus log P, while we write down the Kullback-Leibler divergence and connect it to entropy. And then I think I'll quit and we'll pick back up on Kullback-Leibler divergence on Thursday. Okay. So I don't know why I've been saying Kullback-Leibler divergence all throughout this lecture. Most times we would just say KL divergence and save ourselves tongue twisting. But just to remind everyone, we did this, I think the first time we did it was probably with VAEs. It looks like follows. This is just like two vertical bars to separate P and Q, but the divergence, KL divergence between P and Q. P and Q are two probability distributions, meaning either discrete things like mass, probability mass functions, or continuous things, they would be probability density functions. This works for both. And these are two different random variables, of course, really. So P and Q are distributions, if you will, or densities or masses functions for two different random variables. And so we're going to take an expected value, and because we got two random variables, we better specify which one we're taking the average over is the P distribution. And then the thing we're taking the expected value of is the log of the P density over the Q density. Okay. And let me write it out in the discrete case. This would look like a sum over I of P of xi log P of xi Q of xi. Okay. The continuous case, I would just take this sum, change it to an integral, and the xi outcomes, discrete outcomes, such as x outcomes, and have dx there, I'm integrating over x. Okay, but otherwise this would look the same, right? Okay. And let me just really quickly since I'm out of time here, expand this just to make a point and connect it to entropy. This is P of xi log P of xi. And this is minus P of xi. This is all in the sum. Actually, sorry, let me just make the sum twice, just for P of xi log Q of xi. Okay. Notice this guy is just the negative of this guy over here. So this is just the negative entropy of the X with the P distribution. Let me call it the XP P distribution. Okay, actually, let me just call it P. I think usually we just write entropy of, but you know what I mean, it's the random variable associated with P. The entropy of that. And this term is called the cross entropy. This is what we optimize, minimize in classifiers almost always. At the end of the day, last outputs, you minimize very typically the cross entropy. But in Kovac-Wheeler divergence, is cross entropy, which is usually written as H P comma Q. The cross entropy between the P and the Q distribution is a piece of the Kovac-Wheeler divergence. So I'm out of time, but the point I'll just start with here that they'll set us up with the definition and the connection to entropy for KL divergence is that it's really the entropy of one of the random variables, negative the entropy of one random variable, plus the cross entropy of the two random variables. Okay. Yeah, we'll pick back up on, I'll put this back up and we'll start here on Thursday. Thanks, everybody.